Great. All right. Welcome, everybody, to the AOS Department seminar. It is my pleasure to introduce Ali Vizcarra today, who will be presenting the work that she's been doing that's contributing to her sort of master's degree. Ali got a bachelor's in applied math from UC Davis in 2022, and then went on to work at NASA Langley for a year. And while at UC Davis, I think took a course on in atmospheric sciences and climate, got interested in climate in general, and applied here for to come in 2023, and showed and indicated that she was interested in ENSO. And so I was excited to read her application and say and have a spot in our group for that. So she came and joined AOS in fall 2023 and jumped right in. I think I threw you straight into the fire with a reading group on linear inverse modeling in her first semester here, and then immediately jumping into a course in advanced coupled ocean atmosphere interactions in her first year. And so she has been here since 2003 working on ENSO and various and looking at seasonality events and variability, which we'll talk about a little bit here today. Ali has been active in our GSA and has been a great presence on the 11th floor. Her particular corner of the office is probably the best decorated. I don't know if it says the best decorated student office in the entire building, but the style sense is, she sets the bar high on that. She also sets the bar high in her baking, and we all benefit from that with little gifts of focaccia bread on Wednesdays, I think. She kind of look forward to. And is active outside of AOS as well with a variety of different things. I'm sure we will see pictures of her birds Elvis and Roki. I do like that your bird's name is Elvis. So without further ado, this is Ali. Please. We're looking forward to your talk.
Thank you. Okay. Thanks, Dan. Can everybody hear me okay? Great. So thank you for being here. So I'm excited to present the work that I have been progressing for the past couple of years, and I'm excited to talk about ENSO and the LIM today. So here's a roadmap of what I'll be talking about today. We'll first start off with some introductory material. I'll give a crash course on ENSO, and then diving into what a linear inverse model is, and then its cyclostationary extension. And then the next two sections will focus on answering the research questions that I will aim to answer for the rest of the talk, and I'll show those questions very briefly in the next slide before wrapping it all up in some conclusions, discussions that could lead to future work. So here are the two research questions I aim to answer. I don't expect you to remember this right now, but they are here just to kind of keep in the back of your head as I go through my introductory slides. So first starting off with the first question, which is comparing the two models, and then the second will focus on the noise term that is in both of those models, and if we can link that noise term to something physical. So with that being said, let us first start off with our introductory material and going through some ENSO crash course. So ENSO is an abbreviation for the El Niño Southern Oscillation, and it is the largest mode of climate variability in the world that occurs in the tropical Pacific. And below is an image that's taken from NASA, and this is like the structure that you think of when you hear ENSO. So on the left is El Niño, which shows the anomalously warm sea surface temperatures that extend from the eastern Pacific across almost all of the ocean basin. And on the right is La Niña, where it has that same structure, but with anomalously cool sea surface temperatures. It is an oceanic atmospheric coupled system, where the El Niño part is the large-scale oceanic warming or cooling, and the Southern Oscillation is the atmospheric part of ENSO, where it describes the changes in the Walker circulation. So the warm phase of ENSO is just called El Niño, and here we have two schematics from NOAA, where the one on the left is what the tropical Pacific looks like under normal conditions, and on the right is what that same region looks like during an El Niño. And here we see that the easterly trade winds that blow across the equator get weaker. The oceanic response to those weakening trades would be a deepening of the thermocline, or it's that separation of warm surface water with colder deep water in the East Pacific that is due to a decrease in upwelling. And with that deepened thermocline, we get a weaker zonal SST gradient, meaning that sea surface temperature across the central and eastern Pacific would be warmer than normal. And this in turn would affect the Walker circulation that is indicated by those vertical arrows here. So the normal rising motion that's over the maritime continent get anomalously weaker, so less rainfall. And since the central and eastern Pacific are anomalously warmer, then that rising branch of the Walker circulation will follow, and there will be more rainfall in that region. So here's like a little summary from those two figures that is showing a feedback loop, also called the Bjerknes feedback, and that shows with weakened trades, that affects the thermocline by making it deeper and flatter due to a decrease in upwelling. And the deepened thermocline then causes a weaker zonal SST gradient, so the central and eastern Pacific get warmer than normal, which in turn affects the Walker circulation, so there would be anomalously more rainfall in the central and eastern Pacific. So now when we look at the cold phase of ENSO, also called a La Niña, the opposite effect happens where the easterly trade winds are now stronger, and that pushes those warm SSTs towards the west, piling up around the maritime continent. And with all this warm water piling up, the Walker circulation strengthens, and you get even more rainfall than normal in this region. And another result from those stronger trades is that there is an increase in upwelling in the eastern Pacific, and that causes the thermocline to be more steeper than normal and bringing those colder, deeper water closer to the surface. And then that causes a stronger zonal SST gradient where the eastern Pacific is now colder than normal while the west is warm. And so once again, for continuity purposes, with the Bjerknes feedback, stronger trades lead to an increase in upwelling, causing the thermocline to steepen. That then causes a stronger zonal SST gradient where it's warmer in the west and cooler in the east. And that, of course, affects convection because of the strengthened Walker circulation. So the seasonality of ENSO is that it has a periodicity of 3 to 7 years, meaning that going from one El Niño to the next takes that amount of time. And this is a time series from Copernicus of all the ENSO events since 1993, based on the Niño 3.4 index, which is indicated by that figure on the right. And that's just a region where people usually use to calculate ENSO intensity based on sea surface temperatures. And so the threshold for classifying those ENSO events based on Niño 3.4 are when SSTs are above plus or minus 0.4 degrees Celsius. And we can see here we had a few strong El Niños, most notably the 1997, the 2015, and more recently the 2024 event we just had. ENSO is also phase locked, and that means that events peak in the northern hemisphere winter and are weakest in the spring. And this can be shown with this figure that I made that's inspired by Desser et al. 2012. That's showing the standard deviation of SST in the Niño 3.4 region. And we can see this phase locking of events happen. So we see the peak occur from November to January, which is when the variance is the highest. And then after winter, events decay rapidly through the spring, reaching its weakest amplitude from April to June. And once spring has passed, the system tends to recharge and grow again, setting the stage for the next ENSO phase to occur. And since ENSO is the largest mode of climate variability, it has impacts across all different types of scales. So for example, on planetary scales, it has connections with other modes of climate variability, and it can be attributed to being drivers of one another, such as the Madden-Julian oscillation, the North Atlantic oscillation, Rossby wave trains, the Pacific meridional mode, and many, many more. ENSO also has impacts on more synoptic scale patterns, such as large-scale precipitation, which can be attributed by the strengthening or the weakening of the Walker circulation. The jet stream and storm tracks are also affected by ENSO. So for example, during an El Niño, There is an extension of the jet, which can affect weather patterns across North America. And it also has impacts on much more smaller and regional scales. It has big impacts on farming and agriculture. The changes in SST affect marine ecosystems and wildlife, especially coral, and also stemming from marine ecosystems, and so can have a big impact on my advisor's favorite hobby, which is fishing. And with how much ENSO impacts the globe, forecasting is a big topic of ongoing research. And there are two types of models that make ENSO forecasts, which are these two figures here on the screen, and these are from the IRI. The figure on the left are physics-based dynamical models, and the one on the right are statistics-based models. And the difference between the two is that for dynamical models, they simulate the physics of the atmosphere and the ocean. It solves equations for temperature, winds, and other atmospheric and oceanic variables. They need an initial condition plus full knowledge of physical laws in order to simulate what could produce different El Niño events. But for statistical models, they used, like the name suggests, statistical methods like linear regression or EOF-based analysis to make predictions by learning patterns from past observations. And the two models I mentioned very briefly in the beginning fall under right here. And then we'll go into our next section, which is talking about the linear inverse model and its cyclostationary extension. Before we begin, I'd like to issue a math warning. So let's go ahead and put on our math caps and dive right in. So a linear inverse model, or a LIM, is a statistical framework that estimates the linear approximation of the full nonlinear dynamical system. So what that means is that when you have a nonlinear system like ENSO that has complex feedbacks between the atmosphere and the ocean, under a LIM framework, it assumes that small anomalies like SST perturbations grow or decay linearly with time. So mathematically, the LIM can be expressed as dx dt equals Lx plus zeta, where x is your state vector, so that contains the variables you want to input, such as SST or sea surface height. L is the dynamical systems matrix, which contain the physics of the system based on the state vector. And zeta is the noise forcing, which is all the other stuff that is not in L. Now, historically, a lot of people who like to explain the LIM like to use what's called the fluctuation-dissipation relation, where we can rewrite all these terms in the equation in terms of its covariance matrices, and then the homogeneous solution will give us like these terms, and then L and G are obtained using inverse methods, also known as like where the LIM comes from, and then Q is like a buy one, get one when you set the time tendency equals 0. However, I feel like explaining it that way will make you super confused and will feel lost for the rest of the presentation, and I don't think that's beneficial for either of us. So instead of doing that, I think it's more meaningful to take a huge step back and explain the LIM in a way that's more digestible. So you'll leave here thinking, wow, so that's what that LIM does. So now let's recall something that we're pretty familiar with, which is linear regression. So let's suppose that you have a bunch of data points on an XY grid where X is your predictor and Y is what you want to predict. You draw this best fit line that tries to go through all the points, and of course you have some deviations from this line. So your equation for that would be Y equals AX plus epsilon, where AX is your slope and epsilon are those deviations. And you can expand the slope of the linear regression as the covariance of x and y over the variance of x. And essentially what this is all showing is the best linear prediction of y given x. So now let's change it up a bit, and instead of an xy, we have x of t on the x-axis that represents the climate system at some time t. It could be today. And x of t plus tau represents the climate system at a later time, t plus tau. And once again, we still have our best fit line. We have those deviations still. But now instead of the linear regression equation that we saw previously, we can just rewrite that as x of t plus tau equals g of tau times x of t plus zeta. And we can, of course, expand that g term as the variance of the climate system, the covariance of the climate system over the variance, which is basically just an autoregression for the state vector x. So which means that if we connect the dots, the limb is just what I like to call very fancy multivariate linear regression that is applied through time. It predicts the future state as a linear transformation of the present plus some noise. And what's cool about that is that this is the analytical solution to the limb. However, there is a drawback for this model in which that a forecast only depends on what state you start from, not from what time of year you start in. So the limb is looking for what are the patterns at the time the forecast was initialized. In addition, the L and zeta terms have no seasonal dependence and are assumed to be constant in time. In other words, the limb treats the climate system as if it has no preferred season. So going back to my linear regression analogy, there's only one best fit slope and one pattern of residual variability. So for example, if you initialize the limb in January or September, but both months have those same initial states, the limb will produce identical forecasts for both months. And this isn't good for trying to predict a system that has seasonally varying dynamics like ENSO. So how do we fix that? And that's where the cyclostationary limb is for, or the CSLIM. And once again, mathematically, it can be expressed the same as a limb, but we note that I subscript, where I goes from 1 to 12, referring to the calendar months. Its solution can be expressed similarly, so with those I subscripts. And there's a reason for that, because the intent of the CSLIM is accounting for the seasonally varying dynamics. And so once again, going back to our linear regression analogy, we have that G and zeta are calculated for each month. So rather than having one slope that represents a forecast like the limb, we have 12, one for each month of the year. So that means that a forecast that's initialized in January will evolve much differently than the one that's initialized in September. And that's because the background climate dynamics are different in each season. So to summarize, by comparing the two models side by side, for the limb, once again, you have one slope that represents the forecast, no matter where you initialize it at. So G of tau stays the same. So that means we have this assumption about the limb where, for example, the atmosphere behaves year-round. But for the CSLIM, instead of one slope that represents the forecast, you have 12 different slopes where the system's dynamics depend on the time of year. So just to really put the nail in the coffin between these two models, the limb does not account for the seasonal cycle of a climate system. So G and zeta do not depend on the calendar month. But the CSLIM does take into account of that seasonal cycle. And that's where that I subscript comes in. And so now that we have all the background information, I can now bring up the two research questions that I aim to answer for the rest of the time we have. And it will be split into two parts. Part one will be comparing the two models and investigating the importance of seasonality and ENSO's deterministic dynamics. And then part two will stem from part one, where we investigate the noise term more closely and asking ourselves if we can link that unresolvable, unpredictable term into something more physical and real. And before I begin, I just want to point out that this work is an extension from Aaron Thomas's work, who went through the same analysis as I did 10 years ago, but with the limb only. And here I am now extending that work by using the CSLIM. So shout out to Aaron. So amazing. Let's begin with part one. So before I get into the data that I'll be using, just as a reminder, on the right-hand side, the equations for the limb on the top and the CSLIM right below it. And in order to use these models, I need to construct the state vector x. And so I will be using monthly sea surface temperature from ERA-SysT version 1 and monthly sea surface height, which is a proxy for thermocline depth from ERA-S5. And both data sets are from the time period 1958 to 2022. The data is cosine weighted, and the annual cycle has been removed, and it's taken over the tropical Pacific. Yes?
You've explained everything else so perfectly well, so I'm going to ask you to indulge me. What do you mean by cosine weighted? I'm not familiar.
In grid cells for like data processing, I think, the grid points around the equator are much bigger than like the ones at the poles. So cosine weighting takes into account for that.
Okay,
Yeah.
thanks.
Why did you remove the remove the seasonality of the animal?
I think so you're, sorry, what was the question?
Did you say you removed the annual mean or?
The annual cycle.
That you removed the annual cycle?
Yeah. Yeah. Oops. And here's the region, in case you forgot, which is the tropical Pacific. So thus, the state vector is made by using the first 11 and 5 leading principal components of SST and SSH respectively, and the variance explained for both variables are shown in green. And the reason why we represent SST and SSH by their leading principal components is that we want the state vector to capture the dominant large-scale spatial variability of the climate system, while also keeping the limb computationally tractable and physically interpretable. So to actually compare these two models, we will be using Hovmöller analysis on past ENSO events. So we will be looking at composites of the top 10 strongest ENSO events, which are listed here. And then after that, I will pick out individual strong events. And in this case, it will be the 2015 El Niño and the 2010 La Niña. And so as a reminder, here are the analytical solutions I've mentioned before for both the limb and the CSLIM. And for simplicity's sake, the first term on the right-hand side will be what's called the predictable term, and the second term will be the unpredictable term, in which I will explain in the result slides after this. So let's first start off just by explaining what a Hovmöller is. A Hovmöller is a diagram where it shows how a data field, in which case equatorial sea surface temperature, changes through time. So we are seeing how an El Niño develops in actual observations. We have longitude on the x-axis and time in months on the y-axis, and we are viewing a latitudinally average tropical Pacific, which is indicated by the image below in the red box. There is a black arrow on the right where it shows that we are moving up in time. So starting from the bottom, reading up, the diagram shows that our region is starting to get warmer and warmer until we reach a maximum in the winter months. And then after that, SSDs start to cool down in the springtime. Then by the summer, the El Niño event is already finished, and then we start to see a La Niña starting to form in the following months. So now that we know what actual observations look like, let's see how the LIM forecasts the event that's initialized in January. And just as a note here, we are only focused on the predictable part of the forecast, which is indicated by the shading, and also at the top of the screen. So if we compare the January forecast to what actually happened, the LIM is thinking that this region is just going to be a little bit warm. So now let's initialize the model again, but now in March. So this horizontal black line is our new starting point, and the LIM makes the forecast from that point. And we can see a bit more improvement compared to January, but it's still a relatively weak forecast. So if I reveal the rest of the row, where I rerun the LIM again and again at different initial conditions, we can see as we get closer to the peak of the event, we get better forecasts. So by the September initial condition, the SST evolution looks almost like observations. So let's compare that to the CSLIM. Here we see a significant difference between the two models and how they forecast the deterministic or the predictable part of the SST. So looking at the March initial condition, the CSLIM is already capturing event development pretty clearly. And by May, it's giving a really solid forecast, whereas the LIM took around the September and even July initial condition to capture that growth, peak, and decay to that same magnitude. So where does the noise come in? Well, if we were to start back with our first example, initializing the model in January, we just see an excessive amount of contours. And I'd like to note here that positive noise are the solid lines and negative noise are in dashed lines. And so the noise is obtained by taking what actually happened minus the LIM forecast that's initialized in January. And what's left over is the noise, which are indicated by those contours. So what this is saying is that according to the LIM, the development of an El Niño that's initialized in January is due to unexplainable or unpredictable processes. And that goes the same. And the same goes when we look at the rest of the LIM forecast. So revealing the rest of the row, we see that we just see a lot of noise contours throughout each forecast. That means that the LIM thinks that there are unresolvable processes that help drive event development, which are shown here in this purple box, and it's also trying to shut it down, which is indicated by that green box. And this is especially when we initialize it close to the event peak. So once again, looking at the CSLIM, there is not as much noise contours in comparison to the LIM. And that is because from what I've shown in the introductory material, that the CSLIM takes into account of ENSO's seasonally varying dynamics. And we can see as we run the models at different initial conditions, the CSLIM just does an overall better job at capturing ENSO's seasonality than the LIM. And so the key takeaway from this figure is that the LIM aliases that seasonal growth and decay as noise. And it can especially be seen when I highlight these regions here in the purple and in the green. So now, moving on to the La Niña composites, we can still see that for the LIM, it took all the way until the September initial condition for the deterministic forecast to look like the observed. So the shading looks like the observed. And so the model still thinks that the growth and decay of La Niña is due to noise. And in addition, we also see the September initial condition specifically that even though that the forecast is deterministic, the LIM is trying to shut off the event as noted by that positive contour. Meanwhile, in the CSLIM, the deterministic forecast is already quite accurate by May in capturing that deterministic growth, peak, and decay. And the following forecasts from there just get better and better as you increment the initial conditions. So once again, we can say that the LIM is also aliasing the seasonal growth and decay as noise for La Niña events as well. And so now that we're moving on from composites, and now we're looking at individual events, we are currently looking at the LIM and CSLIM forecast for the 2015 El Niño. And although, yes, we can still see that the LIM is aliasing that growth and decay as noise, this is not the main result of this figure. So in this pink box, I'm highlighting the role of noise forcing here. And this is mainly when you look at the CSLIM, so the bottom row. In this box, you can see that in the March initial conditions, when you look at the shading, were insufficient to produce this strong El Niño. But by July, that had completely changed, in which the forecast for this event is now completely deterministic. So again, the forecast is now looking like observations. It is questionable for how in such a short amount of time between initializing the models between March and July, there's just this dramatic change of the noise from being a driver to event development to just the noise contours completely disappearing almost altogether. So that means something must have happened between the March and July initial conditions where the noise is responsible for nudging the system and producing that strong El Niño. The exact same thing can be said for the 2010 La Niña case where, once again, if I put this pink box over these specific forecast, that's at different initial conditions, we can see that once again, the shading in March were insufficient to produce that strong La Niña and instead are explained by those negative contours that you see here. But by July, the negative noise contours completely disappears and the forecast is almost completely deterministic. And we can come to the same conclusion that between the March and July initial conditions, the noise was responsible for nudging the system and producing this strong La Niña. So wrapping up all the parts from part one, we have first found that from our composites, the LIM misrepresents ENSO's seasonally varying growth and decay as noise. But since the CSLIM does include that growth and decay, this model was able to appropriately capture the deterministic evolution. And just from looking at those two individual ENSO events I've shown previously, we found that between the March and July initial conditions, the noise was responsible for kickstarting the development of these events. And this is a good segue to part two of my talk, which is investigating the noise term itself. And then again, this is a reminder. The question that I aim to answer is that, can we link this noise to something more physical and real, and how can we interpret that? So in terms of data, I'm using daily data instead of monthly from 1993 to 2022, and that is because noise is occurring on rapid timescales. So in order to estimate that noise, we have to use daily data. And then once again, I'm constructing my state vector, and we're using the same variables as before, so sea surface temperature from OISST and SSH from GLORIES 12 version 1. Again, the data is cosine weighted, and the annual cycle has been removed over the tropical Pacific. And then the data below, I'm also going to be using mean sea level pressure and 10-meter surface wind anomalies from ERA 5, and I'm going to explain why we need those in the next couple slides. But just for clarity, these atmospheric variables are not going into my state vector. So how do we estimate the noise in observations? We just use the models themselves to filter out the deterministic evolution. And just as a note, we will only be using noise that is estimated from the CSLIM because of the results we found from part 1. And so once again, here's the equation for the CSLIM, and essentially we're just rearranging the equation. So we're separating out that noise term zeta to the other side. We transform the time tendency dxdt into a center difference, and then the deterministic term Lx is subtracted off. And what we're left is a raw estimation of the noise over a 30-year period that's acting on my state vector. So in order to see what this noise looks like spatially, I will be doing regression maps. So in order to do that, I am projecting the estimated noise onto optimal spatial patterns that will grow towards an El Niño or an ENSO event by December. So December is my final state. This gives me a time series for that optimal spatial pattern, and then I regress that noise time series onto those sea level pressure and 10-meter surface wind anomalies in order to see if we can obtain a spatial pattern. And since I can't show all of my regression maps in this presentation, we're just going to look at February, which is a wintertime month, and June, which is a summertime month. And just a note, if you see the term L2 in the title of my maps, that just means maximum growth that leads to an ENSO event. So here we have regression maps of the noise onto the atmospheric structures with February on the left and June on the right. The contours are sea level pressure anomalies per 1 standard deviation of noise forcing, and the little arrows that you can see are the wind vectors. And so these are, once again, the regression maps of noise against SLP and the winds. We can first see in February that there is this dipole of sea level pressure in the northern hemisphere, which we suspected to be the North Pacific Oscillation. And then that said pattern then disappears in June. And that makes sense because if this is the NPO, then this is a wintertime pattern. We also see an emergence of westerly winds in June that is not seen in February. And this is important because westerly wind events, according to previous literature, such as Eisenman et al. 2005, can precede or even trigger eastward propagating oceanic Kelvin waves that deepen the thermocline, which initiate an El Niño event. And since the arrows are really small on these maps, I want to look at the winds more closely, and I will move on to the next slide, which is just doing a correlation map between the projected noise itself and zonal winds. And what we find is that there is almost no correlation in February, but when you look at June, the correlation is relatively high. And from the following point I made in the previous slide, an emergence of westerly wind anomalies in June indicate that the optimal structure can precede or trigger these ENSO events. And so far, we can see from just these couple plots that the noise exhibits some seasonality. And now that we've seen what the noise structure looks like that optimally grow towards a big El Niño event, we can take it one step further by also looking at what those noise structures look like that lead to specific types of ENSO events. So this is a figure from Takahashi et al. 2011 showing an Eastern Pacific ENSO on the left and a Central Pacific ENSO on the right. And the difference between the two is just the location of SST. So for Eastern Pacific or EP ENSO, the warming is confined to the Eastern Pacific, and for Central Pacific or CP ENSO, the warming is in the Central Pacific. With that being said, here are what the spatial regression patterns look like in February. And here we have EP ENSO on the left and CP ENSO on the right. And we can see, just like in the L2 plots we've seen previously, there is that dipole of sea level pressure in the northern Pacific in both of these maps. And just a little qualitatively, we can see that the NPO structure is just ever so slightly important for CP events compared to EP events, because we can see that the amplitude is just a little bit higher. And then, of course, nothing exciting happening with the winds just yet, but just a little bit of a note, we also see a symmetric dipole, in the southern hemisphere just off the Chilean coast. Now, when we look at June, we see once again that NPO structure has completely disappeared. And once again, this makes sense because the NPO is a wintertime pattern. Both EP and CP exhibit westerly wind anomaly patterns across the equatorial Pacific. But the key difference between the two lie in the southern hemisphere, where for EP events, there is this large dominant signal, more specifically the Southeast Pacific low that we see off that Chilean coast. And then for CP events, we can see that this is a Rossby wave train-like pattern. And this just goes to show that, once again, that there is some seasonality to these noise structures. So to wrap up the second part of my talk, were we able to link the noise to a physical process? The overall answer is yes, because we were able to obtain atmospheric structures that could lead to optimal ENSO development, and there's even seasonality to these structures because, thanks to the CSLIM. And we saw that in all cases, L2, EP, and CP, there is an NPO structure in February that disappears in June. We also saw westerly wind events occurring in June as well. For EP events specifically, we saw a dominant Southeast Pacific low off the Chilean coast. And for CP, we saw the NPO structure in February just being a little bit more important than EP because in previous literature, this is consistent of how NPO can drive CP ENSO events. And then also we saw a wave pattern in the southern hemisphere as well. And so here's an overall summary of my talk. So once again, from part 1, the LIM aliases the seasonal growth and decay of ENSO as noise. But since the CSLIM includes ENSO seasonality, it was able to capture that event pretty good. And then when looking at individual events, we have seen that noise plays a role in ENSO development between the March and July initial state. And then that leads into part 2 of my talk of were we able to even link the noise term from the models into something physical? Yes, we were. And there's even seasonality to the noise. So like in my previous slide, once again, the NPO pattern is shown in the wintertime, then disappears in the summer, and then westerly wind anomalies in June. And then extending from that, we were also able to look at noise structures leading to specific types of ENSO patterns, which is the EP and the CP, and that also exhibits some seasonality. In terms of future work, I am still working on those regression maps, but I would like to introduce additional atmospheric variables such as heat fluxes, so whether atmospheric heating or cooling contribute to ocean excitation, precipitation, which is a proxy for vertical motion, outgoing long-wave radiation, because that relates to convective systems and cloud coverage. And the second point is, since the regression maps we looked at are for optimal structures leading towards an ENSO event, I want to be able to see what those structures look like for individual ENSO years, so like the 2015 and the 2010 events. I also want to explore state-dependent noise, and what that means is that the statistics of the noise forcing change with time of the system, because currently both models assume Gaussian white noise. And then finally, just for funsies, I want to train the CSLIM on climate models and be able to explore other climate modes and how it predicts those climate modes. Whew. All right, now before getting into an entire list of people that I want to thank, I have an honorable mention. I want to thank Mr. King Arthur himself, because this is the best bread flour, not sponsored, although I wish I was, because I've spent hundreds of dollars baking bread, and without Mr. King Arthur, I wouldn't be able to make bread like this for the department. All right, so now getting into the whole list of people, I want to thank the man, the myth, the legend himself, DJ Vimont. Thank you for being such an amazing advisor to me and for all the Dan lore that I have been blessed with for the past 2 years. I also, by extension, want to thank the Vimont Lab Group, which is Joff, Katie, Jack, Zager, and Noah. I also want to thank my committee, Hannah and Myra. I want to thank Erin Thomas, whose work, once again, I've extended my work based on hers. Matt Newman and Melissa Breeden, who are also collaborators on this project. My favorite IT guys, Pete and Kevin, for downloading MATLAB onto my computer and for also renewing my license, because literally without you guys, I would not be able to present my work. I also want to give a special shout out to Rudra, Prem, and Evan for just being great people to talk about the LIM with, and just for able to build on ideas of how to explain the LIM to a broader audience. I also want to thank my partner Kate for just being a beacon of unconditional support, and also for listening to this talk like 100 times. I also want to thank all the faculty and friends I made at AOS, my day ones, Sophia, Idamis, and Shane, and my ride or dies, Ian and Giselle. I also want to thank my parents, my 2 siblings, Amber and Audrey, and the rest of my friends and family back home in the Bay. And of course, like Dan mentioned in the beginning, my 2 chickens, Roki and Elvis. So with that being said, I'll take any questions.
I'll let Allie go ahead and call on folks, but we typically allow students a chance to ask questions first, and then so any questions?
Jack?
This might be like a little bit outside, the scope of your work, but I'm just curious. Have you what is something that maybe you think you're missing in terms of a physical model, or a LIM or not LIM? And so predictions in a physical model might be able to provide that maybe your LIM stuff might not be able to.
Are you talking about in terms of comparing physics-based models to
It's totally okay if you're I don't know, I don't do any of that.
I'm actually not quite sure, because I'm not all too familiar with physics-based models, other than you just put stuff in it and it spits out oh, look, this is what happens when you input these things and it turns into an ENSO. So I'm actually not quite sure. So
I wouldn't know either. That's my
Apologies if this was covered, but were LIM and CSLIM things that you built yourself? Or was that
Oh no, the LIM is based on Hasselman model, right?
You did build them yourself.
I mean, I did
based
build
on
them myself,
code.
but yeah, I made the model in MATLAB and then I ran it. But historically, the math comes from the paper by Pellin and Schwartzmark, where it explains oh, this is the LIM, and it breaks down into its different components, so it's easier to run on the computer, if that makes sense to you.
The math and sort of the theory about stochastic dynamical modeling and how you do that in a multivariate system is developed elsewhere. We apply that, and then we've developed the seasonal version of that here. At the end of the day, it looks like linear regression, right? Which is a great way of describing it. I'd never before seen the practice talk here, but Ali did a great job explaining that. But underneath that linear regression, there's a whole sort of theory of stochastic dynamical modeling that allows you to interpret these things. Yeah, good question.
Grant?
You briefly mentioned using a non-Gaussian white noise.
Yeah.
Have you had a chance to look at SSTs or SSNGC if they PDFs that look non-Gaussian?
I know in the LIM the noise is Gaussian white noise, but I don't think I've done enough exploration enough to explore the non-Gaussianness of it. Evan?
maybe even a more specific question that you could probably do really quickly would be, is your noise estimation that you showed in the second part, that you estimated through the center differencing, is that noise non-Gaussian? Because that's coming from observation, so you could look at it and see
Right.
how close to Gaussian it is, and if it's way off, then that would be a good reason
That's a good point, yeah.
to use some sort of non-Gaussian noise.
Thank you. John?
My question's kind of related. First of all, fantastic talk. Thank you, Allie, for inviting me into the LIM world. I say that because so many times I've heard about this, and there's no disrespect to other people who have presented it before, but no one's explained it as well as you did. No one's explained it to a dummy like me as well as you did. So I really, really appreciate that. That makes me able to ask what I rarely get to say. I don't think it's quite as naive a question as I usually ask, but it's going to be close. And it's related to Grant's question and then Evan's follow-up. Is it possible now for you to say that not all noise is the same kind of noise?
Yeah.
And then you could start to differentiate, and you could really separate the stuff that absolutely is beyond, pulling it in out of the observations. And does that refine your ability to look at subsequent events in the predictive mode?
I like to say I think so, yeah. Especially like the regression maps that I showed were just for, those were for optimal, like idealized structures that lead to an ENSO event. So like what are those optimal initial conditions look like? And then that's not true for individual ENSO events. And so that's another thing that I like to explore is like what do those like individual years even look like in order to see like what the model is representing the noise term in terms of like external atmospheric variables.
Okay, thanks.
Of course.
I think this is a good question. And getting back to your question as well, like the underlying theory behind all of this comes from Hasselman, 70s. I mean, he's winning the Nobel Prize for it. And so the underlying theory behind all this, when we say noise, that comes from an idea that the rapidly evolving nonlinear is the stuff that we study all the time. When you average over a long enough time period, the central limit theorem allows, central limit?
Yeah.
Did I say that right? Yeah. Allows us to approximate that as Gaussian noise. It's not really noise. There's everything John studies, right, is noise, right, according to that average. But in there, there's all that structure to it. And so what's exciting is that this, by being able to link that to the spatial structures, we can start taking synoptic views of individual ENSO events and say,
that's what I'm wondering.
yeah, when did a particular physical process actually kick the system in such a way that
Right.
now there's going to be an El Nino event.
Yeah.
Now there's information in those initial states.
Yeah.
And that's where, there's a lot more that needs to be done for that.
But you can make that refinement. It sure looks like you can begin to do that, right?
Yeah, so
Yeah,
linking
that's exciting.
and getting beyond this idea of thinking of noise as just like random stuff to recognizing that really what we're doing is we're making an approximation to all of those rapidly growing structures that we can't resolve in a simple model like this.
Very cool.
Angela?
Yeah, so I was kind of going to build off on that because I know you chose a couple years in particular to
Yeah.
start some analysis. Were those because they were particularly extreme or really hard to predict, or do those go hand in hand?
Oh, they were just like really strong events that I've chosen, yeah.
Because that kind of ties back to what we're talking about.
Yeah.
Like, if you were to look at cases that were maybe harder to predict, can you tie it back to some noise that was maybe
Right.
particularly different that year, if that's kind of how you're thinking of approaching it? Or
Yeah, I just first start off with the strongest events just to see if we were able to like even like get anything from this, and we were able to. And then I did look at the more weaker El Nino years, and they do like have that same like structure of like the limb is aliasing that noise and the CSLIM's not. But the years I chose in particular were able to really capture like the differences between the two models. So those were why I chose those 2 years like specifically, yeah. Yes, Brad?
So this, I think this is really just a clarification question. You said that with the data that you used to build the CSLIM, you removed the annual cycle. The CSLIM is accounting for the annual cycle. So why did you remove the annual cycle?
It's, I think, in terms of like when building the state vector, because we use principal components and we want to see for each mode of variability, like the dominant structures in UF1 and UF2. And I think removing the annual cycle will be able to give us those patterns within the state vector in order to use those models.
So the CSLIM is still, it's capturing the interannual variability at the right month.
Right,
But you remove the annual cycle just because otherwise it'd be the dominant view.
right, yeah.
Well, think about, yeah, the other way to think about these is, think about a Taylor expansion around the state that's out there right now. And the way a synoptic storm is going to grow around a January jet is very different than the way a synoptic system is going to grow around a June jet. And so by removing the annual cycle, we're removing the June jet and the annual jet and the July jet, but we're not removing the lagged covariances. So the way that system, the variability grows around that mean state. The LIM doesn't distinguish any of that. The CSLIM is able to distinguish how the system grows around that mean state. So you don't need the actual annual cycle in there. All you need is for the variability to be growing differently, the dynamics themselves to be different.
That helps.
Yes, Leo?
Clarifying question as well, but with the construction of a limb and a CSLIM, do they assume like stationary in your training data set? I forget how
Yeah,
it
so-
was, but like,
Mhm.
was that just an assumption you make that the underlying dynamics are stationary? And if so, how robust do you think the limb and the CSLIM would be?
Right.
Applying to the future as our climate activities?
Yeah, so I actually have a slide here where if you assume that if you change the limb into its covariance matrix like form, which is like instead of dx, it's like d covariance of like the initial state to all that, we set that time tendency equal to 0, and that's assuming like the limb is stationary just by ascending, like we're in steady state basically. And the CSLIM is a bit harder a little bit because we can't assume the time tendency equal to 0 because it's different. We're calculating it for each month, but the limb is like, oh, you set that equal to 0 and we assume stationarity by construction, yeah. Mm-hmm.
Kind of a follow up on that. If you do that, and then you diagnose your noise term from to develop your LOX, then is there going to be a secular trend in the noise?
What trend in the noise?
A linear trend, a trend over time that's
Yeah.
because of the non-stationarity of it? And have you looked at that?
I
Does the noise evolve?
Yeah, I think I have a little bit in the second part, and there is a warming trend, I think, in the second PC, but for, not in the noise though, yeah, just for the state vector itself, yeah.
You plotted the actual time series of noise, or very huge trends.
From the daily?
Plot the noise, yeah, the daily noise.
Oh yeah, it looks, hold on, I got it, it's right here. Where's the trend? It's very noisy.
The trend is actually in the state vector itself, so it does take the dynamics of the trend into account.
Evan?
I got another one. This is a thought as much as a question. So in part one, you're estimating the noise by just taking the difference between
Right,
your
yeah.
prediction and then the observed value.
Yeah.
So you're using observations for that, and you have some number of them. But you can also run the limb to create synthetic data, and you could run it really fast. You could create thousands of ENSO events. My question is if you did that and then you went and looked in the limb at all of the strong ENSO events that you created synthetically, which should have some sort of distribution that's
Right.
similar to observations,
Mhm.
do you see the noise always playing an important role in the growing part of ENSO in the same way that it seems like the comparison with the observations that you're making indicates?
I think I'd say so. I think so. Just from intuition, I just think so, yeah.
Yeah. Have you run the synthetic?
No.
I think that would be really interesting to look at.
That would be. Thank you, Evan.
And stay tuned for future work that Joff will be. Awesome. Let's thank Ellie one more time. There may still be some chocolate chip cookies and brownies, and thank you to everybody who brought and the Lucia as well. Thank you.